In the previous video, we explored the inverse function idea. And the key thing that I want you to remember as we're moving forward with this video is that the inverse function f inverse of f undoes the original function f of x. So what we're going to talk about in this video is how we go about the process of finding the inverse of a one-to-one function if it's not a super simple function where you could just do it by reverse engineering the rule. So the first thing that I want to do in this video is I want to talk to you guys about something called the composition idea. So let's say that we have two functions, f inverse of x and f of x, okay? And let's say that we have an input. So here comes x. Okay. And f acts upon it, and it outputs f of x. But what I'm going to write here is it outputs y or f of x interchangeably, right? So we have had instances where we call the output of a function y. We have had instances where we call the output of a function f of x. They have meant the same thing in different contexts for us. But now, rather than stopping here, right, so again, we're talking about the composition idea, y is now going to go through f inverse. So we're looking to see what happens when you compose f with f inverse. Now, remember, I just want to sort of keep us on track here. What this piece of the picture tells us is that f sends x to y. Well, what did we say before about the relationship between f and f inverse? If f sends x to y, well then f inverse has to send y back to x. So what we're going to see here is that in fact, f inverse of y, which is the same thing as f inverse of f of x, is just x again. So what we're seeing in this second stage of the composition process is that f inverse sends y back to x. Okay, so this picture shows us that f inverse composed with f is equal to x. One thing that you might have experienced and gotten used to with composition is that you don't get the same thing when you compose in different directions. So let's see what happens here. So this is going to feel a little uncomfortable at first because we haven't thought about it in this direction. But I think as soon as we talk about it, you'll realize that this is, of course, how it should be, right? So let's say that instead of passing through f first, x passes through f inverse first. So it comes out as f inverse of x, and again, let's call it y, just to have two different approaches to thinking about it. Now watch what we see here. What we're seeing here is, in this first stage, that f inverse takes x and sends it to y. So here's how I'm going to do this. I'm going to put x here and y here, and I'm going to say f inverse sends x to y. Of course, it doesn't matter what order I write the arrows, but I think this order will make it feel more familiar to you. Again, rather than stop here, we're going to keep going. And we're going to compose f inverse with f. Okay, well, what happens here? We know from our previous lesson that whatever f does, f inverse undoes, and vice versa. They close the circle. So if f inverse is sending x to y, that must be because f sends y to x. So sure enough, when y is now going to drop into f and f is going to act on it, what's going to come out? So of course, this is f of f inverse of x. That's good old composition. But once again, that is x. So what we're seeing here that's sort of unusual is it doesn't matter which direction you compose the two functions. And I'm going to write that here. If you compose f with its inverse in either direction, you end up back with x. So you will get x. And we'll do an example of this a little bit later on, but what this does for us is it gives us a really, really kind of algebraically oriented way to think about what the inverse relationship is. So I actually want to use this to do our first example. So let's say that we have f of x is equal to 2 over x minus 7. So I'm going to put a little asterisk here, and I'm going to say this is a one-to-one function. And we're going to have a little lesson more deeply on one-to-one functions next, but for now we're going to assume that this is a one-to-one function, and we're not going to worry about why or how you would know that or anything like that. We'll talk about that later. So find f inverse of x. So I'm going to write here, find f inverse of x. Well, I don't know what it is, but whatever it is, if I compose f with f inverse, I get x back. Now, you all know compositions. So I can write here f composed with f inverse. Whatever f inverse is x. I know that to be true because they're inverse functions. But you also know that the way composition works is anywhere that you see x in the original function is replaced with the function that you're composing with. So f of f inverse of x, that's 2 over f inverse of x minus 7. And that's supposed to be equal to x. So while I don't have the inverse function yet, I know that this must be true. So what we're going to do in the next few lines here is we're going to solve this for f inverse of x. And we're going to do it exactly the same way as if f inverse of x were like a letter, like y or x, and we wanted to get it by itself. So we're going to start by multiplying both sides by f inverse of x minus 7. So I'm going to write that here. Multiply both sides by f inverse of x minus 7. So on the left, we'll have 2. On the right, we'll have x times f inverse of x minus 7. Then we'll distribute, because remember, we want f inverse of x by itself. So we have 2 is equal to x, f inverse of x minus 7x. And again, we want f inverse of x by itself. So we'll add 7x to both sides. So we have 2 plus 7x is equal to x, f inverse of x. And lastly, we'll divide both sides by x. And so we have f inverse of x is equal to 2 plus 7x over x. If you wanted, you could write this as 2 over x plus 7. So I'm going to write that because, oops, I want you to make sure that you're not thinking, oh, you can just cancel out the x's, because all of 2 plus 7x is being divided by x, not just the 7x. All right, just to make sure that you're all believing this, right, let's do a test. So I'm not going to do very many of them. You can do more for yourself. But let's look at f of 3, okay? So f of 3 is going to be 2 over 3 minus 7, which is 2 over negative 4, which is negative 1/2. It's a fraction, that's okay. What we're seeing here right now is that f takes 3 and sends it to negative 1/2. That is what f does. So what should happen is that f inverse should send negative 1/2 over to 3. Well, let's see. F inverse of negative 1/2 is 2 plus 7 times negative 1/2 over negative 1/2, which is 7 times negative 1/2, that's negative 3.5, so it's 2 minus 3.5 divided by negative 1/2. Up here, when we subtract, we have negative 1/2 over, negative 1.5 over negative 1/2. Sure enough, dividing by 1/2 is the same thing as multiplying by 2. The negatives cancel, and sure enough, we get that f inverse of 1/2 is equal to 3. So it is believable, and I encourage you to do more to convince yourself that in fact, the function f inverse of x equals 2 plus 7x over x is the inverse of the function f of x is equal to 2 over x minus 7. Now, in the next, on the next page, I want to look at an example that some of you might find to be a little bit cleaner, okay? So recall, graphically, the graph of f inverse consists of sort of the same points. I'm putting that in quotes because of course that's not totally true as the graph of f, just with the order of the coordinates reversed. So again, we see that same theme that f inverse reverses the role of inputs and outputs. What were inputs for f are the outputs of f inverse. What were the outputs for f are the inputs of f inverse. So what you'll hear said a lot at this juncture is it's like x and y are reversed or flipped. Again, we are talking about all of the same ideas that we were talking about in the previous lesson and in the previous page, but this just abbreviates it, right? So let's look at an example. So say that we have the following function. Say we have 3x minus 5 over x plus 2. Okay, so this is a one-to-one function. And again, I'm going to do a little lesson next about, okay, can we say some more about one-to-one functions? Because they're important in their own right. But for now, we'll just kind of say, okay, fine, it's a one-to-one function. We'll move on from there. So what this means on a graph is that if you look at the graph of f of x, the y coordinates will be obtained by doing this to the value of the x coordinate. So the y coordinate of a point whose x coordinate is x is 3x minus 5 over x plus 2. So as far as f inverse is concerned, So I don't know what f inverse of x is yet. Like, we'll figure that out. But as far as f inverse is concerned, the relationship between x and y is reversed. So the exact same relationship holds, but x and y are reversed. So what we're going to do in the next few steps is we're going to solve this for y. And that's going to allow us to fill in this blank. What is f inverse of x? Okay, here we go. So we're going to do this much the same way that we did the previous example. My goal is to get y by itself on one side. So the first step is we're going to multiply both sides by y plus 2. I'm going to write that here. And of course, what that will do is it will eliminate the y plus 2 in the denominator on the right. And then on the left, we'll have to distribute. So we have x times y plus 2 is equal to 3y minus 5. Distributing on the left, we have xy plus 2x is equal to 3y minus 5. And remember, the goal is to solve for y. So what I'm going to do is I'm going to take all of the terms that have y's in them and group them to one side, and then all of the terms that don't and group them to the other. So here's how I'm going to outline it. I'm going to circle the y terms in one color, and then I'm going to circle the non-y terms in another color. Okay? It doesn't matter what side you put which. So just for the sake of argument, I'll put the y terms all on the left and all the x terms on the right. So what that gets me is it gets me xy minus 3y is equal to negative 2x minus 5. Part of the point of doing this was that so that everything on the right-hand side has a y in it. And of course, if every term has something in it, we can factor that out. So the left-hand side becomes y times x minus 3 is equal to negative 2x minus 5. And now we'll divide both sides by x minus 3, and we have y is equal to negative 2x minus 5 over x minus 3. And that is my inverse function. Now, before I write it up top, I just want some of you maybe thinking, that's an awful lot of negatives up in the numerator. So if you want, you can factor that negative out, like so. Oops. And you can leave it like this if you want to, or for an even cleaner look, you can move the negative into the denominator, so it's not just knocking around. So what you end up with is 2x plus 5 on top, and then distributing the negative in the denominator, you have 3 minus x in the denominator. So we have 2x plus 5 over 3 minus x. So that is the inverse function there. Let's do a little test just to say we did. Okay, so we'll do it here because I really want to keep emphasizing this idea. So let's do f of, well, let's do f of 2. Why not? So we have 3x minus 5, that's 6 minus 5 over 2 plus 2. So that's 1/4. Okay. So what we're seeing here is that f sends 2 to 1/4. So what we're really hoping for here is that f inverse of a quarter is 2. That f inverse sends a quarter back to 2. Okay, so here we go. We have f inverse here, right? We've worked it out. It's 2x plus 5 over 3 minus x. So we have 2 times a quarter plus 5 over 3 minus a quarter. So this is 2 times a quarter is a half. So we have 5 1/2. And then 3 minus a quarter is 2 3/4. So I have to do this division, and for the purposes of this division, it's useful to write things as improper fractions. 5 1/2 is 11 halves, and we're dividing that by 2 3/4, which is 11 quarters. And what I hope you remember is that dividing by a fraction is the same as multiplying by its reciprocal. Oh, look at that. The 11s reduce off. And then the 4 and the 2 reduces with the 4. And we are left with 2. So sure enough, not only did F send 2 to a quarter, but F inverse sends a quarter back to 2. This is the most important idea of inverses. However it is that you find the inverses, whether you're using the composition method, the way that we outlined it here, and believe me, some of you will find this cleaner, whether you're using notationally the composition method or you are using this method that involves switching X and Y. Conceptually, they're the same method. What's at its core is that you realize this is happening. Whatever F does, wherever F sends any input, F inverse should send it back. So this concludes our second lesson on inverse functions, and I hope that you look forward to our next one, which will be a mini lesson on one-to-one functions.